Hello everyone and welcome on today's video. My name is Wouter Pere, I'm the founder and main developer of GHEtool Cloud, and today I'm going to talk to you about how you can convert your EED project or data from an EED project into a GHEtool project. Perhaps you still have an old EED file laying around, or you received the data from a colleague or a competitor of yours, and you want to compare the results with your own calculations. And this is the purpose of this video. So in the first part we will go over all the information that's in the export file of EED, of Earth Energy Designer, and we will translate this to the inputs of GHEtool Cloud. In a second step we're going to compare the results and discuss the differences between both simulation tools. And thirdly, I will end with some final remarks on important distinctions when working with both simulation tools and to get the best results out of it. Let's get started. So now we're in GHEtool Cloud. I've opened a new blank project and I have my EED data on the left. So this is typically an export you can get out of Earth Energy Designer, with all the information that we need to populate our GHEtool Cloud document. So let's get started. In order to compare the results, we always need to set the aim of the simulation to calculate temperature profile. Then we see that the first information we have here is the ground data. So we go to our ground tab and we just can take over those numbers. Now for the ground surface temperature and geothermal heat flux, this is typically selected in a drop-down box of EED, but since the location is not exported directly, we need to go to our custom tab, and then we use the flux data. And we see here we have 9.5 degrees C and 0.08 watts per square meter, and that's the ground data. So then we have the borehole information, which contains information both for the bore fields and for the borehole thermal resistance. So we hop over to our bore field app, and there we see that we have a line configuration, so a 1x10 configuration. You can use a line for that, or we just type a line of 1 to 10. EED always calculates the borehole depth relative to the ground surface. So we keep this as ground surface. We have a borehole depth of 123 meters. We have a borehole spacing of 7 meters. Now in GHEtool we have to enter this for both directions, which for a line of course does not make any difference. But in EED, the spacing in length and width is always the same. So if you want to compare it, for example, with a rectangular field, you have to set both the spacing in the width and the length direction. And then we have here another parameter which is not in the export file of EED, which is the buried depth, namely the depth at which our horizontal piping is installed. So typically this is 0.7 meters. Or if you're drilling under a building, it's perhaps 3 meters or even deeper. It will have some effect on the temperature results in the end, and we will discuss that later in this video. So this is all the information regarding the bore field. Then we have our borehole resistance step, where we can see that we have a W tube. Our thermal conductivity of the pipe is 0.42. We see we have a filling conductivity of 1.5, which is the same. Borehole diameter of 140. And then we have in EED the shank spacing, which is defined as the difference or the distance between the two bends of the U-tube. Now in GHEtool we use the difference between, or the distance between the center of one arm of this bend with regards to the center. So it's half of the shank spacing. So in this case it's 40 millimeters. Next, we have the thermal resistances, which is just informative. We do not need this in GHEtool. Then we have the information about our heat carrier fluid. Here, the same story as with our temperature data from the ground. We select the custom properties, and here we can enter all the information manually. So we have a thermal conductivity of 0.47, a specific heat capacity of 3930. We have a density of 1029. We have a dynamic viscosity in kilogram per meter seconds, and we have a flow rate per borehole of 23 liters per second. The freezing point is not an input parameter, it's also informative there. So this was everything related to the borehole thermal resistance. The next information we need to enter is the thermal demand. So this is the information for the base load and the peak load. So we always use a building load with a monthly resolution in this case. Let's start with setting the seasonal performance factors. So for heating it's 5 and for cooling it's 10,000 or 100,000. Now setting it this high means that you almost assume that passive cooling is ideal, meaning there is no electricity consumption, the efficiency is near to, or not near to, but very, very high. Personally, I often use more realistic values like 20, 25 to account for the energy consumption for your primary circulation pump. But it's up to you to decide. If we want to make the comparison, we keep it at 100,000. Next, we see that we have no annual domestic heating load, so we set that to 0. And then we have two options for the monthly load. You see here that all the heat load and the cooling load is given for every month. So if we want to make the comparison, we should set our load type to absolute. And here we can enter the loads for every month. So that would be in both peak and base load, so there are 48 different values, which I'm just going to type. And with the magic of editing, we will be back when this is finished. So now I've entered all the information in the monthly loads tab, all the monthly heating and cooling loads in megawatt hours, and the peak loads in both January and February. The only thing that we needed to enter was the peak duration in heating and cooling. Now in EED this is given for every month. In GHEtool you only need to enter it once, and it's the highest value. So for heating the highest value is 36, and in cooling it was 8 hours. And then we have here below the number of simulation years that we can enter in the general tab, as I did here, and it is 50 years in this case. So let's go ahead and calculate the results and compare them with EED and see if we can spot any differences. So here we are. This is our temperature profile we get when we convert the EED data into GHEtool. And we see that we have a minimum average fluid temperature at the end of minus 2.03 Celsius. And we have a Reynolds number of 2408. So if we scroll to the calculated values in the export, we see our Reynolds number is the same. But we see that our peak load in heating, it goes to only minus 1.5. So there is quite a big difference between GHEtool and EED there. Now, most of this difference can be explained by the effective borehole thermal resistance. So in EED this is 0.7675, and in GHEtool it's quite a lot higher. It's 0.0984. Now, how this is possible? As you perhaps can recall from an earlier video, there is between the laminar and the turbulent flow there is a transient regime. As you can see here, the Reynolds number of 2408 is in the transient regime, so it's not quite that turbulent, the flow, and that's why the value in GHEtool is closer to the laminar flow, whereas EED assumes that after 2300 Reynolds it's immediately fully turbulent. So this value is very optimistic, and the value from GHEtool is more realistic because it takes into account the transient flow. Now, if we would say, well, what would be the results if we make abstraction of the borehole thermal resistance? So if we go to the borehole resistance tab, we go to measured and we just copy and paste this value. Then we directly calculate with the effective values from EED. We will still see a difference, because now we are at minus 1.26 degrees Celsius, which is more optimistic than EED. So how is that possible? Now we can explain that by going back to our bore field tab. As I said, the bury depth is a parameter that's not mentioned in EED or not required in EED, because EED assumes that your ground surface is insulated. So there is no heat transfer between the environment or the environment temperature and the ground in your bore field. With GHEtool we use another model where we can take this effect into account. So by setting a bury depth, we can estimate how much energy over the decades is transferred between the environmental temperature and your bore field, which leads to smaller impact of the ground imbalance. So that's why we have a slightly better result here in the end, whereas EED is a little bit more conservative on that side. Now there is another thing I just wanted to mention. If we go back to our first scenario, to our borehole resistance step, we now entered the fluid data with custom parameters. Now in EED you have a list where you can select your antifreeze and the percentage of antifreeze, etc. And then it will give you back these numbers. But if you recall, the thermal conductivity and the viscosity, etc. is dependent on your temperature of your fluid. And perhaps the temperature at which these values are calculated in EED is not your design temperature or your minimum temperature threshold. So that's why if you know the percentage of antifreeze and what antifreeze you can use, I would suggest you go to the water X tab and you type it in with the percentages itself, so that GHEtool can calculate which values are the most relevant for your particular project or your particular design. But if you just want to compare EED with GHEtool, it's better to type them over directly to get a fair comparison of both. So that's what I wanted to say about how you can convert your EED data in order to populate a GHEtool project. If you think this video was interesting, please leave a like or subscribe to the channel, share it with your colleagues, and I'm looking forward to seeing you in the next video. Take care. Bye.